Okay, welcome everyone. Tonight we're going to be talking about software-defined radio. You might see it referenced as SDR, software-defined radio. You may have heard me speaking with the other group about this before, but I wanted it on record so I can post it to our YouTube site. So we'll not probably as deep a dive as I've done in the past, but we'll cover it again in some detail. Plus, I got a little more diagrams and pictures in tonight's presentation for those people that prefer to see those things. But as always, first we'll do the news. This weekend is the Fort Lauderdale Air Show on Fort Lauderdale Beach, and Helen and I will be there along about 10 a.m. tomorrow and be there until they end in the afternoon. We'll be in the drop zone on the beach if you're looking for us. Look for a tacky, cheap, red and white striped umbrella, 6 foot in diameter. We'll be under that.
Holes in it. No holes?
No holes yet. But if the wind starts running up, I probably will just whip out my knife and take a slice into the top of the umbrella just to let the wind out so it doesn't invert itself. So I noticed that there's a conflict. There is a Vero Beach air show this weekend as well, along Vero Beach. And they divided it up. We get the Air Force, they get the Navy. So the Thunderbirds are here and the Blue Angels are up there. Or maybe I got that backwards. Anyway, the Air Force team is down here and the Navy team is up there. Some sad news to report. I don't know if you noticed it, but a couple of months back when I was talking about the results of the decadal survey that the U.S. uses to identify what scientific endeavors they want to spend congressionally approved money on. Turns out they don't want to spend money on SOFIA. They got so many other irons in the fire with James Webb and the things that follow that. They looked at the cost to operate versus net science discovery and concluded that we don't need to spend money on the airplane if we've got spacecraft and millions of dollars invested in telescopes on the ground. They just completely missed the point regarding what SOFIA is capable of doing. And when they took the money away, they went back to the German government, DLR, and said, fine, you want to keep SOFIA flying? You pay the entire tab. And the German government said, we agree, there's no money in this endeavor. So SOFIA will be shut down towards the end of September of this year. Yeah, sad to see her go. But here's the interesting part. This is not the first aircraft that has been used for astronomical observing. There were 3 others that preceded it. And NASA still has all of those in mothballs.
In the same hangar where SOFIA is.
Yeah, so I'm guessing that they're shutting down SOFIA operations and they're going to basically put a lock on the door on the hangar that SOFIA and all of the other aircraft observatories are located, and maybe get back to it in the future or refer to it as museum items or something, but it won't be flight worthy after a few years of lack of maintenance.
From what I saw during the time of my mission, even the ones that are not used often, they were being maintained. I don't think they will let it, they will mothball it, reduce the stuff, but I don't think they will let it go to waste. Because in the same hangar, they have the, ER2s, that are still used for testing satellites and stuff. Yeah. So I think they still, my hope is that they still gonna do some minimum maintenance.
Well, my hope is, if you remember in the hangar, they have those airplanes that will not be spoken of, the Global Hawk, the clandestine surveillance planes they got from the Air Force by way of the National Reconnaissance Office, and they still have those, and they are using them as rapid deploy unmanned aircraft for weather observation. much like they do for the U-2, but it costs less to operate
The
them.
R2 is not a U2 anymore.
Yes, I know they made a couple of modifications, but to me, they'll always be U-2s and they'll always be SR-71s and things like that. But I think they're going to take the Global Hawks and see if there's some way they can very inexpensively do smaller diameter infrared astronomy with them. But that's just what I'm hoping. We'll see. They could do those on a shoestring budget, a little sidebar money. No big deal. Won't be billions. Anyway, sad to see her go. And I attended the online conference regarding NASA's 2022 Summer Astrophoto Challenge. And they picked a target, and the target is a nebula, and it's the Carina Nebula in near Eta Carina, in the Carina, the ship's keel constellation. Unfortunately, we can't see it from South Florida, except all the way down in the Florida Keys, and then you get to see it about 10 degrees above the horizon for a short period of time. But the NASA Astrophoto Challenges don't require you to own a telescope or a camera. You can actually use their robotic, if you sign up to be part of the photo challenge, you can use their robotic telescopes that Harvard University maintains for their astronomy students. So you can sign up for time on that. But even better, this is more of a photo processing challenge for artistic creativity than it is a natural realism photo contest. So all those pretty pictures that are false colored and exotic and collages and such, that's really what NASA's looking for. So you can actually do a data mining on NASA's archives of the Carina Nebula, and then merge some, pick different colors, learn how to use the online tools, and then submit that. So for those people that just want to learn how to play around with pixels in pictures, you don't have to actually submit what you produce. You can actually sign up to submit, play around with the tools and the online imaging and stuff like that, and then just not submit it. So if you're looking to have fun with pixels, here's a way to do it. And the JWST now has full focus on all instruments. And I thought this picture, which is actually a collage, it's not a real picture, was interesting. This is very similar to a picture that I presented during our James Webb Space Telescope presentation. This shows the total field of view of the telescope instrument and its mirror system. And it shows you all the individual instruments that can capture photons. So you can see NIRSpec, NIRCam, MIRI, NIRISIS, and the fine guidance sensors. Now you'll notice that they're all looking at slightly different parts of the sky, because the mirror that directs the light to the imaging chips directs it to all the chips at the same time, so they don't have to worry about focusing on a per chip basis. They can get them all in the same focal plane. So you'll see that, oh look, looks like a galaxy down here, there's a bright star there, there's a completely different part of the sky here and here and here, and then over here there's a string of stars. It looks like a nebula. So when you think about the requests for use of the observatory, what target do you want to look at? Well, I want to look at a particular galaxy like this one. Okay, we'll put that galaxy in, what camera do you want to use? I want to use MIRI. So we'll position it so that that galaxy is in the center of field of view of MIRI, and then anybody else that's made a request that would put what they want to see in the other instruments will be simultaneously captured. The fine guidance sensors are really just looking for a few stars. They just need a pattern of stars to do their guiding, basically, like a guider on an amateur astronomy telescope. Now, NIRIS is one of the spectroscopic imagers, and you might have seen some close-up images of these shutters. And if you remember, we had a micro image showing a stylus tip poking at one of the shutters during the presentation. And there's like 10,000 plus individual shutters. It will either allow light to come in from a spot or will block it, so they can obscure bright stars while doing longer duration exposures on dimmer stars, which is rather clever, but they're not the first to do that. Spitzer had the same capability in its rudimentary form with fewer shutters. But they showed that some of the shutters, here's the first, it's broken and there's nothing you can do about it on the Webb telescope. Some of the shutters are stuck open, some of the shutters are stuck closed. They can't control the shutters. So there are some actual broken bits on the Webb, and the shutters are the first thing that they would come out and say, yep, some shutters aren't working as expected. Don't quite know why, but anyway. So the web blog pages is where to go to look at the latest stuff. I actually was strolling through YouTube and saw Dr. Becky coverage of this and how she was so excited that they could see pictures. And she never pointed out that, yes, this is the field of view of the telescope, but there's no camera inside the telescope to take this picture. So what they do is they take the individual images from the sensors and then they glue them all together in this collage, so they can show you what all the instruments are seeing at the same time. Anyway, that's the Webb as of now. Okay, massive announcement about something at the center of our Milky Way galaxy. If you remember, the Event Horizon telescope took a radio image of the black hole at the center of M82. Why didn't they take one of the black holes at the center of our galaxy? Well, as it turns out, the black hole at M82 is 1,000 times farther away, but 1,000 times larger than our black hole. So they used M81.
Basically, because the black hole is munching something, then
yes,
you cannot
they used
observe.
the black hole. They used the black hole at the other galaxy as a test target to prove that what they were doing with the very large baseline of radio telescopes could actually do what they expected it to do. And now that they've got that under their belt, they're going to come back and within the next, so 2 weeks, I'll say within the next month maybe, they're going to produce a similar sort of image of the black hole at the center of the Milky Way. Now, why didn't they do that initially? They had the same camera capability from the radio astronomy. It's not actually an optical camera, it's a radio camera. They had exactly the same capability, and if what they were shooting was 1,000 times farther away but 1,000 times bigger, it was the right size for imaging. The problem is our black hole has junk around it, you know, debris field that is actually absorbing in infrared and re-radiating. So our black hole is actually more difficult to spot from the background noise. So they feel that they've made advancements in the algorithms for post-processing to the point where that will no longer present a problem. But anyway, look out for this in another couple of weeks. We'll probably do it on a Saturday night and mention, look, it looks identical to the one at M82, when it shouldn't. Think about it for a moment. M82 is tilted almost 80 degrees to our plane of our solar system. So it's real easy to take a picture of the whole aspect of the black hole in M82. But if we're looking across to the black hole at the center of our galaxy, it's pretty much parallel to the plane of our solar system by about 8 degrees.
Basically, if you want to see a whole of a CD or a DVD disc,
yeah,
and you're looking from this point of view, you won't be able to see it because you have the material of the disc right in front of your eyes. You need to actually have some angle for you to see the whole.
And that will be my telltale of, are they spoofing us? If they show a lovely hole like this one, where were you at when you took this picture? Oh, you were above the plane of the galaxy. I get it. Do we have any spacecraft?
No. It's Getty telescopes.
Right, right. We have
It's
no,
a Getty images, so it's Getty telescope.
yes, we have no astronomical instruments, no spacecraft of any kind that are above the plane of our solar system, let alone the galaxy.
Oh, by the way, Monroe, can you clarify a little bit? That's interesting thing to do is explain what is the Event Horizon Telescope, because this is an amazing thing.
The Event Horizon Telescope, their goal is to capture imagery of the event horizon of a black hole. And the way they do this is they need to have a very, very tight field of view, very small fractions of an arc second field of view at very high resolution. You cannot do that with any individual optical telescope that is currently now deployed. It's just not feasible. So what they do is they do imaging in radio. They gather all the data across a large number of telescopes spread as far across the Earth globe as they can, and then they do post-processing on it to create a synthetic aperture telescope that is a good portion of the diameter of the Earth. And that's how they get their extremely high, accurate, high resolution, very tiny field of view imagery.
And the other interesting things is how much data they need to carry. They cannot transmit the data. They need to fly the data because it's petabytes.
They're capturing essentially 5 petabytes of data per day when they're observing at each one of the telescopes, which is why it takes years to process this stuff, because you'll do a day of processing. You'll take all of the solid state disk drives out of the array of computers, and then you'll put those in a giant crate, put that on a pallet, and then ship that to the VLA for post-processing. And you'll do that for a number of months, and now you have all the data there, and then you will gradually load all that data into the system, pre-process it down to a smaller volume of data by throwing away all the junk, all the out of range stuff, to try and get it from 5 petabytes per observing session down to maybe only hundreds of terabytes per observing session per telescope. And then you'll process across all that data and come away with, a 3,000 by 2,000 pixel single image. And this is actually an artist rendering. See, illustration, it's not actually the picture. People look at that and go, how did they take that picture? They didn't. Some guy with watercolors did that. And, oh no, Pluto is in retrograde. This changes everything. So the astrology folks are trying to make meaning of Pluto is in retrograde. What does that mean for my sign? Pluto is in Capricorn. What does that mean for my sign? Well, my sign is Capricorn, if you believe in such stuff. Now for the science facts. Pluto goes into retrograde for a number of months every year. So take a chill pill, folks.
And by the way, all the traditional astrology traditions all over the world never even mention Uranus and Neptune. Just imagine mentioning Pluto. That is only the visible planets were part of all the traditional astrology.
Because people started dabbling in astrology before we found all the rest of the planets.
Well, that's science, right? Now that they know about the additional planets, they can add it to astrology, right?
Yes, and NASA even added the 13th sign of the zodiac, which astrologers do not respect.
I am Ophiuchus.
No, what's the 13th sign?
Ophiuchus.
Ophiuchus.
And therefore, if you were born under that sign, you're an Ophiucan.
Serpent bearer.
Yes, so if you're a Scorpio, you may not be a Scorpio. You may actually be an Ophiucan.
Or a Sagittarian.
Yeah, because it splits right down through the center of the
between Sagittarius and
zodiac. Yeah.
Right now, at this moment, in the years that we are in the last 2,000 years, is about between Sagittarius and Scorpius, and it's right in the center of the galaxy. And the date falls around the last days of November and the first days of December.
Yeah. Well, Pluto will be in retrograde from April 29th through October 8th of this year. So the first commercial astronaut program to the space station was successful after 17 days. They came back on Monday of this week, landed in the Atlantic Ocean off of Florida. So this looks good for the future of commercial astronautical programs.
And this suit is awesome.
Yes, their spacesuit looks very futuristic and slimline, as opposed to the big bulky things that NASA produced. That's what happens when you rethink things and you can use modern materials and 3D printers.
But not just their suits, everything is like that.
Oh yeah, the Dragon capsule has a lot more room in it than a Soyuz capsule. If you want to talk about legroom in cars, talk about legroom in a capsule. You're in a sardine can in the Soyuz. And also, on Wednesday of this week, they sent 4 NASA astronauts up to the International Space Station.
Oh, someone is back.
The interesting thing is, what did these 2 missions have in common? SpaceX provided the launch vehicle, the capsule, the spacesuits, like pretty much everything, all commercial. They're looking for some other commercial vendor to step in and do what SpaceX does today. And the other companies are going, give us billions and we'll promise to do it in the next 20 years. Like, can't you catch up today? Well, that would cost real money, and we might be interfering with some SpaceX patents, so we can't do that. Besides, we don't want to look alike. They can have black spacesuits. And yesterday there was another 53 Starlink satellites that went up. I did notice that they're cutting short the videos now. It used to be they would have a slot that was open for about an hour and a half for the prior to launch, getting everybody on the video stream, talking about SpaceX as a company, showing all their successes, and then they would show the countdown and the launch, and they'd go through all the various steps of returning the launch vehicle back to the pad or to the boat. They'd show the separation of the satellites, and now it's all like 15 minutes prior to launch, they go on the air, and by 30 minutes after launch, they go off the air. You never actually get to see the satellites anymore. Oh, if you go on the website, you can see a video they shot of the satellites. And I first thought, I believed what they said, which was they're doing this because they don't have good radio coverage where the satellites are being deployed. And I thought, wait a minute, they're deploying satellites in a place where they have no radio coverage from the ground. How do they talk to the satellites? I think it's more a matter of that airtime costs money, and we'll just cut it back. Now, I know that in the case of SpaceX national security missions from the NRO, they are not allowed to show you certain parts of the mission. Like, no, we're not going to let you see the stealthy satellite we're putting up into orbit to monitor the things. I understand that, but for the commercial missions, I think they're just saving money on airtime.
Yeah, I was disappointed when I saw that they said coverage will start in 2 hours or 3 hours. I wanted to see coverage for 3 hours, but I didn't.
Yes, but that coverage is usually people yammering about either what's coming up or what successes they've had, and I want the meat. So I actually watched the video and I skipped the slider forward until I get to like 5 minutes before launch, because I know that entire sequence in there. What's going to be filled, what's going to be shut off, what's going to be started up. And I look for all those markers, and then I watch the launch, and I just want to see the meat of the program. I'm fine with that. In fact, at some point in the future, I'm probably going to get to the point where I don't even watch them live anymore. I just go on YouTube and watch the replay, and then only bits of it. So how many people knew that there was a partial solar eclipse today that could only be seen from southern South America, parts of Antarctica, and out over the Pacific Ocean, and a little bit over the Atlantic Ocean? So couldn't see it from here, which is why there was not a lot of media hoopla about it. Because even a partial eclipse that lets you see it from someplace in the U.S., the media would be crowing about it. Let's just hope you don't have anybody in the administration staring up at solar eclipses anymore without protective glasses. And here's some clickbait. NASA's Mars helicopter discovers alien wreckage on the red planet. You know what it was?
Yeah, the debris.
It wasn't even debris. When Perseverance landed on Mars, there were certain covers that had to come off of the top and bottom of it. This was the bottom cover before they started the landing. So the aliens that deposited this wreckage are humans. The wreckage is discarded bits of the Perseverance landing craft. So we are the aliens and this is our wreck. It looks like a flying saucer.
Yeah. Someone should go and clean that stuff up.
Littering.
So then aliens really do look like us.
That's what I keep trying to tell you. How
And
come we
we're
don't know
already
whether or not the
polluting
aliens are
another
here?
planet.
Yeah, the reason why you
We're
don't know.
already polluting another planet.
Yes, the reason why you don't know whether or not the aliens are already on Earth is they look like us, they sound like us, they act like us. Look for the ones that behave a little out of social order. That's about the only thing they can't quite get right, unless you believe in the Gary 7 philosophy. How many people remember Gary 7? The original Star Trek series?
I remember Gary 7, the cat.
No, he's not.
Yeah,
Gary 7 was the man. The
Yeah, the
cat
weird
was
guy.
Isis. The cat was
Yeah,
Isis.
Yeah.
And
The
in
Robert
the
Lansing.
yes, and Terry Garr, the
Strange
latest
eyes.
Picard series, season 2, actually makes reference to that, because much like this alien race that nobody knows about in the future and can't find their planet, that alien race not only took humans to train them over generations to come back and protect the Earth, they also took Romulans to come back and protect the Earth, because apparently wherever they take them to, it's a big happy coalition of all kinds of alien species. So they took a Romulan back to this planet and over generations trained her to come and protect the Earth timeline. So yeah, being helped out by that.
And what is this philosophy?
The philosophy is we're here to protect the Earth. You'll never know we're here because we look and act just like you. That's the philosophy, is we blend in. We don't stand out, we blend in. So we don't go knocking on the front door to the White House. We just ignore those people.
And you know what? Sometimes when I hear things like that, and just the art in the reality imitating art, it is so weird. Because it's probably
not
what's
weird.
happening now.
It's not weird, it's just plausible.
Yeah. Well,
Yeah.
now even more, because now we know a little bit more.
Well, when things don't work as planned, or when things work better than expected, how would you ever tell that there wasn't an influence? You'd never know, and there'd be no way to prove it. So for example, the James Webb Space Telescope had how many moving parts on it that all worked flawlessly? Given NASA's history? Come on. So it was very reassuring to see that some of the shutters on the spectroscope didn't work.
Mm-hmm.
Okay, so yes, I was in medical device interoperability standards online meetings for several days this week, many hours per day, stretching on into the evening, because they were holding the meetings on the west coast of the U.S. So they didn't care for the fact that, so what if you're, skipping dinner and you're awake until 9 o'clock at night in continuous multi-hour meetings? So I have 3 videos in the pipeline to be processed. So tonight we're going to talk about software-defined radio. Next week we're going to talk about SQUIMs, measuring darkness using a sky quality meter, and how you actually compare all that stuff and how you can do it manually or using instruments.
Do you want me to bring tomorrow mine for you to show and kind of show and tell? So you can.
At the air show?
Yeah, and then you
It's daytime. A swim's not going to do you any good.
To you for you to do a show and tell.
I'm not doing a presentation. I'm a member of the public attending an air show.
No, when you do your presentation, that's the next time I see you in person.
Oh, yes. Bring it tomorrow and I'll get it from you. And I mean, I've got pictures of one, but it's better to actually show it off. And another place that it will be significant is the following week, I'll do a presentation on dark and quiet skies. There are initiatives by multiple organizations for dealing with light pollution and now radio spectrum pollution. So there's an initiative by both the International Dark Sky Association and the International Astronomical Union called Dark and Quiet Skies. Now it's kind of a misnomer.
Are you going to troll them?
Yes.
Okay.
Yes. I'm going to point out the lack of understanding they have for what they're doing, and the fact that they threw in the quiet skies just as like a tack on. But anyway, we'll talk about dark and quiet skies and all the programs that are going on there and what they actually mean, and just ask some questions. I hate it when people say, I'm just asking questions. No, you're not. You're trying to instigate a riot or something. And then the following session, which Dark and Quiet Skies will be our Saturday evening session. And on the Sunday into Monday following that session, I might be doing a live online session, Total Lunar Eclipse, on Sunday evening into Monday morning. And it turns out I now know where I'm going to be doing it from. And our members and the public are unfortunately not invited, because to do so would mean it would require a special use permit, which requires a certificate of liability insurance, which we don't have. So anyway,
you know what you should do? You should do online YouTube after you set up your equipment and see that. And instead for you to record and present, you should do live YouTube.
I plan on doing exactly what we did for the James Webb Space Telescope. The plan is to do a live Zoom session with a bridge over to Facebook Live during the observing of the total eclipse. And that way we have a recording from Zoom for YouTube processing, and we have a recording of the Facebook Live session. And it will be at a place that I can't tell you about, but I could tell Helen tomorrow, because I'd like her to be there. I need somebody to help me with this stuff. I can't spin all the plates at the same time.
Okay.
Good.
I had an idea what to talk about.
Okay, so that's all the news I had. Anybody have any other news to report?
No.
There were a bunch of things in the media, but when I drilled down, I found out this is just a rehashing of something from several years ago, and I think we already covered that, so I didn't bring those up, but they were good for clickbait. It's always fun to look at those YouTube videos and you go, I've already seen that, and then you look at the date on it. Yeah, that came out 2 years ago. They're just bubbling it up to the surface to get more hits on it, which, by the way, our James Webb Space Telescope YouTube video is now up to over 1,300 views.
Wow.
Slowly but surely. So anything before I start the presentation? Good evening. Tonight's presentation is on software-defined radio, or SDR, software-defined radio. People may have heard me blathering about SDRs and radio astronomy previously under a different organization, but I'm kind of redoing this updated one so that we have one that we can post on our Broward Astronomy YouTube channel. So if you've heard some of these things before, you're not having a deja vu moment. You are hearing them again. So amateur radio astronomy. You can observe and capture images in wavelengths of light, visible light, infrared light, narrowband, which is hydrogen alpha or sulfur or oxygen 3. The electromagnetic spectrum has all kinds of photons at different wavelengths, and you can get equipment that will allow you to capture those photons and then convert them to pictures, and you can process them. But you can also observe in radio wavelengths. So well below infrared and even well above even radio bands. You can look in the high end of ultraviolet into X-ray and gamma. But we're just going to focus down in the radio, which is below light. So it's obviously not visible to human beings, otherwise we would go a bit crazy because there's radio emissions all over the place, and it's good that we can't see them. But a single radio observing station is unable to make pretty pictures of stellar objects because we're basically just sampling signal frequency and amplitude over time. So you get the squiggly until you collect a lot of data and then you post-process it, and now you can get pictures. But in order to capture radio wavelength data, you need a high gain directional antenna, something called a Yagi. It looks like an arrowhead. Or for a narrower field of view with a stronger signal, you can use a parabolic dish. And people have taken those old 12-foot and 6-foot satellite TV dishes and repurposed those. They've repurposed DirecTV satellite dishes, but they can't quite do that with the current ones because the current ones are not circular. They're just a slice of an antenna. They're like an orange slice shaped antenna. And you need a bracket to mount that antenna to go to telescope mount so you can point the antenna. Because if you can't point the antenna, you're just relying upon the Earth rotation to scan the sky, and that can take time, and also you'll scan a lot of stuff that you didn't mean to scan. Now the signal coming in is going to be very, very weak. It's got to pass through the Earth's atmosphere, which makes it even weaker. So you're going to need probably a low noise, high gain amplifier. This is also known as a LNA or a low noise amplifier. And then you need to make the antenna, which is not purpose designed for amateur radio astronomy, to the software defined radio receiver, which is not designed to work with those kinds of antennas. So you need some kind of mating coupler to join the two together. And you don't want a cable between the two because then you'll lose signal over the attenuation of the wire. So you want just a coupler, connector to connector. And then once you have that connected into your SDR, you need to be able to tune it to say, what frequency do you want to listen to? How much bandwidth? What's your signal sampling? All that kinds of stuff. And you'll use an application like SDR Sharp, which is software-defined radio receiver written in Microsoft C#, which is why they call it SDR Sharp. And you can not only look at the live data, you can also record it and then later play it back if you want to do some further analysis. So here's the bits and pieces. On the left, we have the Yagi antenna. It's a Yagi Uda. Most people just refer to it as Yagi, but it's actually a Yagi Uda antenna. Inside here, there's actually two circuit boards with a bunch of copper traces on them, and they're stacked one on top of the other, so it gives you a very wide receiving band, and the copper traces act like amplifying coils to boost the signal amplitude. But that's just the antenna. It has this aluminum bracket on the bottom, or a steel bracket, and then you have to convert that to something that will mount to a telescope. And that's where a dovetail plate comes in. You pick up a dovetail plate, you drill holes through the mounting plate, you put bolts in, and you slap that into your dovetail plate on your, in this case, it's an Ioptron Cube Pro. Now you've got the antenna, it's mounted on a bracket, its bracket's installed on the telescope, on the go-to telescope mount. Now you need to get the signal out. Well, here's the signal, this 1 foot long wire that you run. It's got an N-type connector on it to keep the antenna inexpensive. You screw that into this side, which is an N-type connector, and then it comes out the other side of the physical coupler to an SMA connector. And that's what's on the input side of either a low noise amplifier or the software defined radio. And this is what the LNA looks like. You have power going to it, usually 5 volts or 12 volts, and then analog signal goes in, analog signal goes out, and it gets boosted by this little tiny chip. That chip is smaller than a match head, is the best way to describe it. And then you've got some capacitors and resistors that get rid of any stray signals. But that's optional. If you want to pick up low amplitude pulsars or quasars, you need something like that. You might need 2 of them back to back in line to boost the signal. So the receiver itself, it's the thing that actually converts the frequency and amplitude of the analog radio signal into something digital that can be captured and processed by computers for analysis and display. So even if you always want to listen to only a narrow range of wavelengths, they're going to be emitted at different frequencies. So you need a receiver that can tune it down to that. Years ago, people would have receivers with knobs and dials and little indicators, and it would, using analog means, usually capacitors or resistors, plates of them, to tune the antenna cable and the antenna itself to pick up particular frequencies, and they apply filters to filter it down to just the band that they want to listen to. So it would be a notch filter that would just listen to what you wanted to listen to and nothing else. But that's so yesterday, and the manual tuning stuff, the dials, and those can all be so digitally imprecise. What you really want to use is a computer that you can command digitally to say, here's the exact frequency I want to listen to, and here's how many hertz or cycles per second I want to listen to, and here's the sampling rate, the number of samples per second that I'm going to take of this signal. Well, it turns out there's a fancy thing in electronics called a phase lock loop, or a PLL, that allows you to take a crystal oscillator and then create a loop of the frequency that will allow you to pump the signal you want to receive across that loop, and thereby you can have a tuner, and you can select just the frequency you want because you adjust the phasing of the phase lock loop, and that says only certain frequencies will cross that. And then once you get the frequency across, there are things called automatic gain controls that will always make sure the signal is amplified by a certain level, by a certain amount to get to a certain level. So if you adjust the gain to be, you always want a signal that's 80% of the full range, it will dynamically change the amplifier's gain to always boost the signal so that the peaks are at that level. So this is a very contemporary and fancy way of saying we got rid of a lot of the old bits in analog radios, and now they're more capable, easier to tune, more digitally accurate, and not big. So we're only going to cover receivers in this presentation, not transmitters. I know we've got a amateur radio enthusiast amongst us who has a transmitter and speaks to people using things like ionospheric bounce and moon bounce. And so,
Jack?
Yeah, I don't see him on tonight, but he can watch the video afterwards. So since we get rid of a lot of the components and the packaging, we can shrink the SDR device down to something small. What do we need? Well, we need an input connector for the antenna to connect up to, and we need some resistors to match the resistance of the cable going to the antenna and the antenna itself. We need to have a software commandable frequency agile tuner. That just means I can send a digital value to the tuner and it will tune the center frequency that I'm going to be receiving on. And we can use our phase lock loop to adjust the frequency. But if we just use a simple CAN crystal oscillator, those can change at a very, very small amount as the temperature of the circuit heats up. So what you want is a voltage controlled crystal oscillator. So as the temperature changes, you can change the voltage driving the crystal so that the frequency is more on target. We'll get into a moment on the concept of an intermediate frequency. That's what all receiving and transmitting radios basically use. And then we'll talk about the software-defined radio receiver itself. This is the part within the package. And then you need some way of getting that software-defined radio data out to a computer, or maybe audio out so you can listen to it. do the old Jodie Foster and put the headphones on. Not that real amateur astronomers actually do that stuff. So you can take all these components and package them up into something relatively small, a little bit larger than, let's say, 3 sticks of gum, and the same width and depth of chewing gum. Or you can take these parts and embed them in a much larger package, so they can now use SDR technology as the core of amateur radio transceivers. And I believe that Jack actually has such a piece of equipment in his ham shack. So here it is, and I've actually enlarged it so you can see everything. So on the left, we have our antenna connector, our SMA connector, and on the right, we have a USB 2.0 data connector. So you plug that into the computer, you connect the antenna up to that, and the radio is all in here. All the electronic components for the radio are in here. And you remember me talking about the voltage-controlled oscillator, and it's actually a temperature-compensated crystal oscillator, TCXO. So version 3 has all these different things inside of this device, and you can go to rtl-sdr.com and find out whether they have some of these in stock or not. The chip shortages that have been plaguing the electronics industry has also affected this device. So sometimes they have in stock, sometimes they don't. But assuming you don't get scalped due to the chip shortage, these devices go for about 20 bucks. And they can tune a lot of different bands. They can tune from 24 megahertz all the way up to 1.7 gigahertz. And when you tune on a particular frequency, it can grab a bandwidth around that center frequency of 2.56 megahertz. And what it samples at is 7 data bits. And you're probably thinking, that doesn't sound like a lot. You know, 8 bits would be 0 to 255. So 7 bits is 0 to 128. You can't get a lot of precision in that. But we'll cover how they actually do magical things with that in math. You can take samples up to 2.5 million samples per second. See how that's directly related to the bandwidth? Yeah. Where it's really limited is by the USB 2.0 full or high-speed interface. When you're sampling at 2.5 million samples per second with 2 7-bit or 8-bit bytes per sample, that's about the limit of USB 2.0. Is you're transferring as much as you can out of the pipe. There are SDRs that can transfer much higher data rates than this, but they're nowhere near this cheap, and they're a bit bigger. So what is the SDR device doing on the inside? Well, here's the basic parts. There's a connector to get the data in. There's a tuner to select the frequency and the bandwidth. There's a receiver that actually does the conversion for analog to digital, and then it puts it up on a USB host interface and sends it to the computer. So that's literally the stuff on the inside. Well, let's break that down. What is the tuner? Most people think the tuner is just a chip, and the most popular chip in SDRs is something from a company called Raphael Micro. It's an 820T2. T2 is just the current flavor of it. There are earlier versions of it, but the T2 is the best one. There's actually a low noise amplifier inside there. It's a simple amplifier, but there's a low noise amplifier. There's the phase lock loop. There's the temperature compensated voltage controlled oscillator that produces that intermediate frequency, which is 36.167 megahertz. We'll get to that in a moment. There's a filter that removes frequencies above and below the IF center bandwidth. So it takes 36.167 and says, that's the center. Then it takes our 2.56 and says, that's the widest we can receive. So anything outside of that, just throw it on the floor, filter it out. So it's got coils and stuff to filter that out. Now, once the signal makes its way through the filter, the next thing you want to do is boost the signal again, because you just took out a lot of it, a lot of the energy in the signal when you did the front-end filtering and then the IF conversion. So you boost it up again using a variable gain amplifier. It's variable in that software can control this. Or you can set it to automatic and just say, I want it about there, lock it, and it does that. But generally, you don't use the automatic gain on natural signals like celestial radio sources, because then it distorts their true waveform shape. And remember we talked about the 7 bits? Well, it actually has circuitry that converts the amplitude over time into 2 different signals based upon phase splitting, and the 2 signals are I and Q. So there's a 7-bit I sample and a 7-bit Q sample, and that's the actual data. And then it sends that resultant I and Q data samples to the receiver chip. Now let's talk about that IF, the intermediate frequency. Think of it this way. We've designed the front end, the tuner, to be able to select a center frequency over a very wide range. But we don't want to have to create the electronics to process that wide a bandwidth accurately and with no noise interjected all the way through the back end of the electronics. So what we do is we tune the front, and then we map that onto an intermediate frequency using our phase lock loop. So if the signal changes at the selected frequency, we can actually map that to just the IF, that center frequency, over the bandwidth of what our tuning device is. So that means all the back end can just strip everything out that's not the band around the intermediate frequency, and done. So we tune over the 24 megahertz to 1.66 gigahertz, and then we map that using the phase lock loop to the center frequency of 3.167 megahertz, and we filter everything that's not within our 2.56 megahertz bandwidth. And that's how we get to our samples per second over the USB interfaces. We could crank out more, but we couldn't pass it over the USB interface. It's not fast enough. So if you wanted to look at just the Raphael micro chip, this is what's inside the chip. So it takes in the analog loop data, and you see this loop through. Like, what is that for? That's leftover capability from when this chip was used in a TV tuner box. Back when you had digital television that you could tune on a handheld receiver, that was what you did. You put the antenna up to it, it would send the signal into the computer to decode it, and then if you wanted to send the signal out, you could pull into that, tie into that tap and get your loop through. Well, that's still there. And some of the SDR devices do actually support the loop through. But it takes the broadband, the maximum range of frequencies it can receive, runs that into the phase lock loop as coupled by the voltage controlled or temperature compensated oscillator. It then maps all the received signal that you've chosen onto the intermediate frequency. Once it's mapped to that, it strips out anything that's not the intermediate frequency range. It then runs that through a variable gain amplifier. It then splits the signal by phase into essentially the frequency and amplitude signals. And you can externally control the gain on your variable gain amplifier, so there's got to be a signal for that. And then, of course, there's computer interface signals for commanding the voltage controlled oscillator and the phase lock loop for the tuning. So that's all inside that one little chip, and then the functions inside the receiver. The receiver chip is made by a different company called Realtek, and you might recognize them as, don't they make like Ethernet network chips and Wi-Fi chips and stuff? Yes, they do, but there was a time when they made these chips that were SDR receivers for TV, FM radio tuner boxes, and they're programmable. So you can use them for amateur radio astronomy. So the SDR chip actually receives the analog intermediate frequency, the I and Q signals from the tuner, that previous chip. It then uses 2 analog to digital converters to convert the analog radio signal phase quadrature values into 2 7-bit I and Q values and pumps them into 2 8-bit bytes per sample. So it essentially packages up these 2 7-bit values into 8-bit bytes and then wraps that as a USB block style stream. So it can sample at very high speed. And then it passes that over the USB interface using the fastest possible connection it can get from the hosted computer. And over that same interface, it also receives commands for controlling the receiver and status of the current state of the receiver. And here's what's inside that receiver chip. Here's our 2 signals coming in. They're analog. They go through digital to analog to digital converters. And now you have the 2 samples blocked, packaged up into a data stream. And then that data stream is deposited over the USB interface, and the commands and status get separated out for processing by the components. If you wanted to build a higher capability receiver, this is really all the parts you need, because the tuner could still be the same. You could actually change these 7-bit ADCs into 12-bit. And they're actually devices that have swapped out this chip for their own components to make 12-bit ADCs, and they swap USB 2.0 to USB 3.0, and even Ethernet and USB-C. And so speed on the back end is no longer a constraining item, as are the digital to analog converters. They now make them 12-bit, very much faster. So look for SDRs to get even better as the next few years go along, because these TV tuner chips are going out of stock. They're not going to be making them anymore, and they're using sort of last time buys to get them. So what's this I and Q? What does that actually mean? What it's actually doing is you want the frequency and the amplitude. So it's going to be doing some interesting math on the quadrature phasing of the analog radio signal before it takes the samples to split out the signal phase cosine, which is the I signal, and the signal quadrature sine, which is the Q signal. If you go, wow, here it is. You wanted pictures, here's pictures. So this is your normal waveform. You've got an analog waveform here, sinusoidal. But if you were to turn that on its side, it would kind of look like a corkscrew, because you're not measuring just the up and down. You're actually measuring the up and down as if it were a point on a circular curve, a quadrature. And you can map that into essentially a point that moves around the center of an axis. So you have the I-axis and you have the Q-axis. So you have an imaginary value here, and you have a real number value here. And you measure the angle of it and the amplitude. So from that, you can actually get the frequency and the amplitude of the signal with these 2 very narrow values. So it's playing games with math, but it allows you to sample at a very high rate and use very little data over the bus. So that's quadrature sampling, and the 2 components, the I and the Q, are actually referred to as phasors, because you're analyzing the quadrature phase of the signal. It's not heavy math, but it's interesting math. I knew there was some day when trigonometry would be the savior of us all. And as I was mentioning, chip availability. The 2 chips, the tuner and the receiver, they have their roots all the way back to digital set-top boxes for broadcast and satellite. And they were receiving the ATSC, or the digital TV standard signals, and they could decode those. But with a little bit of firmware and driver changes, you could use those chips to make a good software-defined radio receiver. But there's a new standard on the horizon, ATSC version 3.0, which includes FM digital radio, which the first generation didn't include. And when they add that, they're going to be focusing more on streaming services than they were on broadcast services. So don't expect the ATSC 3.0 chips to be as flexible in using them for software-defined radio. So we'll wait and see, but once these next generation chips come out, they may not be usable for software-defined radio. So we may be stuck with the tuner chip we have, and the receiver chip may go away, and therefore we have to come up with sort of parts put together receivers, but I think there's parts for that. So as long as they can, they've been using some of these obsoleted chips that are in scarce supply. Sometimes you'll find, batches of 10,000 of them or so that have been in some distributor's warehouse for some time, and they'll want to sell them cheaply. So a company that wants to package up these devices like RTLSDR.com will do a last time buy of whatever inventories they can find of chips. But there is another place on the horizon where we might get similar chips. They're not the TV industry or the satellite industry. They're the 4G and 5G radio industry. So as mobile phones get more things integrated into a smaller number of chips inside the phone to reduce the price of the phone, the receiving end, what's inside the tower, has been going from very large circuit boards with lots of components on them to very much smaller circuit boards with fewer and fewer components on them, but they've been asked to support, 4G and 5G and the different bands of 5G. And rather than making separate components for each of those, they said, why don't we take a book out of the SDR manual? And so the chips they're using for 4G and 5G in the cell towers are actually software-defined radios, so they can literally just change the software and, oh, your 4G is now 5G. But only if you buy the right chips to begin with. If you bought fixed function 4G solutions, then there's no amount of software you can update that will get you to 5G, which is why there's a lot of swap out in the towers. So there is a company called Lime Micro that is using chips on the front end, and they're using gate arrays on the back end to define software-defined radios that are much better than these old TV tuner chips. But instead of it being $20, it might be a little over $100 for the packaged board that will do this. But if the RTL-SDR parts go away, I may be looking at getting a Line Micro-based device that was originally intended to be used in 4G and 5G base stations in cell towers, but we'll repurpose it by just changing the software. So here's how all the parts come together to actually make a receiving station. So the antenna mounts to the bracket. The bracket mounts to the telescope mount, the go-to telescope mount. The antenna cable comes from the antenna, goes to an N to SMA coupler. That coupler then gets attached to the SDR USB dongle. There may be an optional LNA between the coupler and the dongle. But then that produces a USB output connection that you then take a short cable and run that to a computer, typically a laptop, because those are portable for field use. And then you run your SDR Sharp software inside the computer, and now it can take the signal coming from the SDR and present that to you in a number of ways using math. So the first thing it does is the computer will filter the data further. It does this using digital filtering. So we can actually take that bandwidth that you took in from your SDR and actually pick a center frequency within that and then narrow that down further and throw away samples that are outside that range. So you can essentially zoom in and get more resolution on the signal data. But that's just the raw signal, frequency and amplitude. But that may be modulated. There may be a signal embedded in that raw frequency and amplitude information that you may demodulate out using software that will convert it to like an FM radio station where you can hear singing and talking and that kind of stuff on the FM band. Or you could tune to amateur radio band and listen to hams. Or you could tune to radio control towers and listen to airport, arrival and departure and taxiing on the ground. You can tune it to weather radio and listen to NOAA weather radio reports. So that's all of the audio stuff you can hear out of there once you demodulate it. But you can demodulate other things like data, computer data. And then you can look at that as not just a waveform signal vertically, that is frequency, gyrations, and amplitude over time. You can also do a rotation of that data called a fast Fourier transform to create something called a waterfall display, where you're looking at the spectral analysis of the waveform. You're looking at frequency over time with amplitude showing as brightness of colors. You can take that raw data and store it digitally for later analysis or playback. And here's what those two types of displays look like. So on the left, we have a spectral display. And you can see that the frequency down along the bottom and the amplitude of the signal along the left. So all these little spikes you see here are variations in amplitude, and the spikes over a particular range is the amplitude over frequency. So if you have amplitude over frequency, that's an amplitude modulated signal. But if you have a signal that's been modulated by frequency over time, that's a frequency modulated or FM signal. That's FM radio, which is, spectral display is okay for looking at that. But if you want to look in radio astronomy, you want to look at the domains, the frequency domain. Where is the frequency coming from, and how does it change over time, and how high is the amplitude of it? So what you do is you do your fast Fourier transform, you reshape the data, rotate it, and now you have frequency over time vertically. So this will actually scroll down the display, and as the frequency changes, you'll see these colors moving in and out like this. And as the amplitude increases, you'll see the brightness changing. It's just two ways of looking at the data. So SDR Sharp, this is an application that runs under Windows that you can freely download from a company called AirSpy. They're the authors of it, and they manage it. The software is written in Microsoft C# programming language. SDR Sharp is developed and maintained by the folks that make the AirSpy models of software-defined radios. I was talking about the RTL SDR being about $20. The AirSpy is around $100. It's a slightly higher capability device that still uses the same chipset, but it's got a few extra bells and whistles. And SDR Sharp is fairly flexible in that it will actually support receiving from a variety of different brands of SDR devices, including the ones from RTL SDR and including the ones from their parent company, AirSpy, as well as some others. But it can not only receive directly coupled SDR through that USB interface, it can actually receive over an Ethernet network connection. So you can actually receive in like a Raspberry Pi computer at a higher speed, clean up the signal there, and then send the received signal across an Ethernet connection, and SDR Sharp knows how to connect up to that and receive that. So you're no longer limited by the performance of your laptop. So you can take a laptop that's less expensive, lower speed, and actually more reliably receive at higher samples per second by offloading the sample conversion in something like a Raspberry Pi, where the SDR is connected up over USB to the Raspberry Pi, and all the Raspberry Pi does all day long, 24/7, is just receiving data, packaging it up into Ethernet packets, and then shipping that across to SDR Sharp on your Windows machine. But SDR Sharp is not a fixed function application. It supports a plugin interface that allows third-party developers to create new capabilities that were not originally envisioned as part of SDR Sharp. So you can have digital automatic gain control. So you can change the signal amplitude as it's processed through SDR Sharp. You can create new kinds of noise reducers. So if you want to reduce a specific frequency of noise or a specific amplitude of noise, you can have plugins that will be noise reducers for that. They're called noise blankers. You can have a different presentation other than the fast Fourier transform waterfall. Or you can take that waterfall, get the source of the plugin, and improve it. And then the one that I'm always looking at is demodulators. If you want to demodulate audio, there's all kinds of freely available and built-in ones for AM radio and FM radio and all of the sideband stuff that hams do. Plus, it can demodulate digital data in the signal. So I don't know how many people have noticed it, but in your car radio, when you're listening in your car radio, you can see scrolling text going along your radio's display if you have a more modern radio that has a digital display on it. And it'll tell you things like what the name of the album is you're listening to, who the artist is, what the name of the individual track is, or advertisements from some lawyer firm. But that's just part of the FM radio signal nowadays. You can listen to aircraft radio. You can listen to them talking on the radio, but they'll also squawk their aircraft ID. And if you use the right kind of antenna, it can actually tell you where those aircraft are. So I've actually took my receiver and run the appropriate plugin where I could see a map of all the aircraft flying around in South Florida, because the FAA requires you to have what is known as a transponder on your aircraft, and their IDs are decodable through open source public plugins. So it can actually show you the aircraft flying around on a map. Good for about 1 hour after you got it all working. You know, we spent hours getting it all working, and then you go, okay, now what can I do with it? That's pretty much it. You're watching aircraft flying around on a map by their ID numbers, and there's mapping software that will allow you to map their ID numbers to the aircraft type, and then you can get the aircraft identifier and map it to the airline, so it'll actually show you what kind of airplane that is and who the parent airline is of that airplane.
I watch it for days on end.
Yeah.
It's addictive.
You watch it for a while, and then you go, I got a life outside this, don't I?
No.
But then again, what do? I give up on that, and I go watch YouTube for hours on end. 6 of one, half a dozen of another. There are scanner plugins. So if you're into listening to police radio or emergency services radio, it can dynamically tune the radio for what frequency you want to listen to. Another thing that it can do is, if you're into listening to satellites, looking for satellites, pointing your radio telescope at a satellite and then tracking it, you can track that signal as it goes across the sky. But as the satellite transmitting comes above the horizon and then goes overhead and goes below the horizon, the Doppler shift of the radio signal will actually change. And there is a plugin called Orbitron that will change the tuner to automatically adjust the received frequency for that minute Doppler shift, which is rather cool. So I've actually listened to, radio signals coming down from satellites. I've picked up signals from weather satellites, and when you combine in the Orbitron with the weather satellite receiving software, you can actually get weather satellite maps every 4 hours if you want to. I think it's a lot easier just to go on the internet and have somebody else pull that down for you and post-process it. And you can get plugins that will remember certain frequencies and bandwidth and modulation, so you can actually create a catalog and then just do like selects from whatever you've titled that entry, and it'll retune the center frequency, change the bandwidth and the modulation, so you can have kind of punch buttons like you do on automobile, old style automobile radio. So in conclusion,
what about astrophotography? How can you make that?
That's the very last bullet item here. So in conclusion, you can do astronomical observing in radio rather than optical. It's another way of peering into the electromagnetic spectrum. There are inexpensive SDR devices that have opened up observing to many more people. And the fact that they can use these chips that are meant for another purpose for radio astronomy is kind of cool, because it means nobody had to spend many millions of dollars to create purposefully designed radio astronomy chips, which might have a market annually in the tens of thousands as opposed to tens of millions, which would mean that chips have no return on investment. So it's good that the chips are out there. They're cheap. There's free software that's available that opens it up to even more people, and there are plugins. And it turns out that there's this whole avenue in radio astronomy called fast radio bursts that astrophysicists haven't quite figured out what these are. There's a couple of postulations out there about what they might be, but so far none of them have been 100% on the money, so they're still guessing. But the best way to figure this out is to get lots of observations. And since fast radio bursts occur out of nowhere for no apparent reason on different frequencies at different parts of the sky, they're heavily relying upon the amateur radio astronomer community to pick these signals up, realize what they are, package up the data, and then send that to professional radio astronomy observatories for inclusion in their processing. And if you get the signal with a certain level of quality, as in accuracy, digital values associated with the sampling, and time, accurate time of day down to a small fraction of a second, your amateur radio observing can actually be used in professional environments to create imagery. And that's the last bullet here. So I've worked extensively in the ability to take multiple radio astronomy receiving stations based upon these inexpensive USB SDRs to create a very long baseline interferometry array to produce radiographical images of galaxies using software from the US's National Radio Astronomy Observatory software project called CASA, which is Common Astronomy, Common Algorithms for Software Astronomy.
Mikasa.
Yeah, Mikasa is Sukasa. They used to call it CASA Core. Now they just call it CASA. But CASA is the software that is used by these very large interferometry arrays like the Event Horizon Space Telescope. And they have different processing lines for doing different radio astronomy observatories. And I could not convince them to put one in there for amateurs. So what I had to do was write software that would take our shoddy data and map it to being better data in the format that CASA could process. And so over there, I've got a Raspberry Pi that's got the CASA Core software loaded on it, and a 1 terabyte software device for storing radio data. And at some point, hopefully, eventually, if I ever find time, I'll finish that project, and then we can take just, anybody that has a SDR USB dongle and a Raspberry Pi and a GPS receiving antenna to get location and high accurate timing signals, and then capture data, and then we can send the data to me, and I can process it through my CASA dedicated Raspberry Pi 4. It'll take days to process the data, but the end result is it should be interesting to see a galaxy or a nebula in radio imaging by inexpensive radio telescope mounts using cheap antennas and $20 receivers, and running that through a Raspberry Pi to produce images. So a very long project, because I'm the only one that's working on it. I knew tonight would be a short session because we've got the Fort Lauderdale air show tomorrow morning, so we can't go too late. I'll have a number of links involving this. So this presentation tonight is more for the people that want to learn more about it without actually doing it. And for those people that want to do something, it's a good starter course if they already understand the very basics of radio astronomy and the electromagnetic spectrum. Comments, questions?
Very nice. Thank you.
So it's for you, just to kind of explain a little bit how you make an image from radio. It's almost like making pictures of like a little squares. So you map the signal and then you end up making, so basic one antenna makes 1 pixel.
Yeah.
And then you need to map a whole area. And then if you have more people with more telescopes in one antenna, you can add that data, and that data can even simulate extra pixels that don't exist. That's what we call interferometry. So if you want to like an image of the sun in the telescope, you need to actually do like a swiping of the sky where you are, and you take a picture. So if you do something like that, I'm gonna try to kind of explain like this. Hold on. Okay. Full signal, full signal, full signal, full signal, and then like half signal, half signal. Okay, so I'm kind of have like little holes that I draw here. My face, I need my face. A little holes that I draw here. It's like if you make like little dots, or you use like squares, like mapping squares, you have like the pictures being like, because it's a round object, like taking a picture in radio of the sun. So you have the middle of the picture would be a strong signal. So you have a strong signal. And then the edges of the sun, when you have like the round part, you would have that to be like a weaker signal. So it's almost like you just seen like squares that make a picture of something that was supposed to be round. So that's basic how you map anything in radio and data. Even when you look at maps of Doppler radar, when you have the weather, when you watch it on TV, if you approximate the data and just zoom in, you see that's pixelated, because basic what you're doing is color by numbers. So radio is basic, like when you do image, it's a mapping of a field, and that field you color the strength of the data, and then you have colored by numbers. So that's basic how you do the pretty pictures. And in that case, you can have, the Doppler for the weather, you map the clouds, or you can map stuff in the sky. Then after post-processing, you can have some images that look like, interesting things. But because it's not visible, it's not a picture. It's actually a data swiping of a field, and then you color coding the data and the strength and the wavelength, and then you have the image. So it's a build-up image.
So whenever you see an antenna and the antenna is perfectly flat, that's called a phased array. And what it actually is doing is there are individual receivers across that array. And think of them as if you had a camera that had a bunch of pixels in it, and you spread all those pixels out over a much larger area, there would be gaps between the pixels. And so what you're doing is you're creating a synthetic aperture. You're basically creating a virtual diameter that is much larger than the actual little pixels themselves. So if you think about the pixels in a camera and you spread those pixels out, you're going to be using interpolation to create synthetic pixels between the pixels. And that's how you get your shape across the antenna. But the antenna is literally flat. If you were to look at a Starlink satellite, a SpaceX Starlink satellite, you'll find that it has no, curved dishes or wireframe antenna booms, anything like that. It's just little flat squares. This is a phased array antenna. So what it's actually doing is it's scanning back and forth very quickly across all those receivers and transmitters to create a very much larger antenna than the diameter would actually look So it's spreading it out. It's creating a synthetic aperture, and it's doing high-speed samplings using interpolation to create points between points. And then it takes all that data in, and then it maps it to an image. So that's how you get an image out of a little squiggly line.
Monroe,
Yes.
this is Joanne, and
Yes.
I have several comments to make, so I'd like you to know what I'm saying and then comment on it, okay?
Okay.
Okay, first is that I think that when I listened to the last time you presented this, we spent a lot of time on the Raspberry Pi 4
Yes.
Raspberry, and you had just gotten it, I think, or
Yes.
less, or and you showed it to us on the screen.
Yep.
And I that was very interesting because I would have never, I had a hard time grasping what the Raspberry Pi was. And,
Oh, okay.
and,
okay. Well, I didn't want to get into the Raspberry Pi so much tonight. I wanted to look at just the software-defined radio itself.
Yeah, and I gather that is why you aren't showing us hands-on. Like I had, even last time when you showed us the Raspberry Pi, and you showed us all those pieces too, it got very complex. It was much more complex than tonight is, in a sense, because you showed us a lot of the pieces. But one of the things that you did show also was, or at least I was trying to figure in my mind how somebody gets interested in this, because learning how to build it before I even see how it comes out, and actually with Helen giving us like the picture of the grid after, was interesting. And I think you had more grids the last time too, as to what the results were. But I still don't, I don't get when you're sitting, if you go in, I picture myself, if I was going to get into this at one time, I would think that I would have to see somebody sitting in front of the machine that gathers all these points or broad bands out there, and then it's like computer generated onto another screen. I gather there's like a monitor and a machine that's gathering all this information, and a machine that it's going to. And so I was trying to figure out how you got interested in it, your story, and then how in general people get interested in it, that they see the machine. Because I don't see me getting into building it. I'm just not a builder like that. And I don't think you have to have the building ability to get interested in it. I maybe I'm wrong. Maybe you have to know all the chips and raspberries and all that.
No, you don't have to know all of it, but you do have to understand the pieces that you need and the processing that has to be done, but you don't have to know the algorithms themselves, because the software for doing the image processing, like I said, is provided free of charge. You do have to build it, but one person can do that and then share it with others. The actual receiver, okay. So
Back, I think, yeah. Not that far. Too far.
yeah, I'm trying to get it in focus. It's hard.
Yeah.
So here's the receiving part, and then there's the USB connection to the computer. That is the tuner and receiver right there in that little box.
It's the whole thing.
That's the whole receiver and tuner. So that takes in your radio data in, and it spits it out as USB data to the computer.
Okay, and you hook that up to something else, though.
I hooked that up to the computer, but on the other side, I hooked that up to an antenna.
Yeah.
Ta-da!
Oh, I did remember the antenna, what it looked like.
The antenna, you can see how big it is.
Well done.
It's fairly thin. And then I mounted a bracket. This is the bracket that comes on the antenna, but that won't work on the telescope mount. I added a what they call a Vixen-style dovetail plate. That's the normal thing that you would use for mounting your telescope in your telescope mount. So it clamps around that, and then you have your coupler. Remember you mentioned the N. There's an N to SMA direct coupler. There's no cable in the middle. And that screws onto the antenna. And then that connects up to
All right.
The SDR device using
Got it all.
using the SMA connector.
Okay, so you could buy both of those pieces, or do you have to have all the skills to build that Raspberry?
Okay, the antenna is, there's no Raspberry Pi here.
Oh, okay.
There's no Raspberry Pi here. The antenna is off the shelf, Amazon. The plate is from Orion, off the shelf, bought it through Amazon. The coupler is off the shelf, bought it through Amazon. The SDR USB dongle, off the shelf, bought it through Amazon. So these are commodity parts, and I think it was, depending upon when you buy it and where you buy it from, the antenna is about 30 to 40 bucks. The plate is, I think that was around 15 bucks. The coupler, you can't buy just one, you got to buy two because that's how they keep the price. And I think it was about $7. The USB dongle, the SDR itself, was about $20. Although I think now they're probably higher priced because of the chip shortage stuff and people feigning chip shortage when there isn't one.
Yeah.
So that's the actual receiving portion. But now you need a telescope go-to mount that can accept a Vixen dovetail plate, because you clamp that into your mount and then you tell your telescope, which is now a radio telescope, not an optical telescope, go point at M82, and it goes and points at M82. And then you use the software that's coming in over the USB, the SDR Sharp, to say, start receiving signal. And now you can look at the squiggly line, or you can tune an FM radio, or you can tune, things where people are talking or music is playing, and get that directly. There's no post-processing. It's just converts the signal, demodulate it, produce the audio.
So you don't need to know anything about how it's
No, there's
done.
no Raspberry Pi involved in that at all. That's just the SDR plugged into USB, plugged into your laptop, and your laptop running the SDR Sharp software. Now, if you wanted,
the thing is that you said there that, I'm sorry to interrupt you, but
go ahead.
I was surprised by, you said you hooked it up to the telescope mount and it directed you tell it where you wanted to go. Now, I'm thinking the telescope mount doesn't have like that in. Does it have some kind of computer that can tell it where to go, the mount itself?
Yeah, if it's what is known as a go-to telescope mount, you'll have a hand controller, and then you can select celestial targets in there. Like if you wanted to go to the M82 galaxy, you would just, line up your telescope, make sure the antenna is connected to it, and then say go to M82, and it would go to M82 and track it.
So are you saying that this is on any telescope mount that people have? Like, my telescope.
Yeah.
Could I substitute that on my mount? Or
no, because your telescope mount does not allow you to swap out the optical telescope for another kind of telescope. It's what is known as a fork mount. So the telescope is actually mounted between two brackets. Now,
what you could do is to install a brace, like a plastic brace, to hold on to the antenna to the tube of the telescope.
No, it'd be too heavy. You couldn't.
Oh, okay.
It's nylon gears, and you couldn't move the existing telescope with the antenna. The weight would be too much.
Okay.
So that's what I was thinking. Okay, thank you. Go on from there. And also, you didn't tell me how you got involved in it. Did you see somebody?
How I got involved in it is when I was a teenager, I had a Whisker radio. I had a crystal radio receiver that I could tune, FM radio stations and AM, and it was essentially a little wire rig that went through some analog stuff to demodulate the circuitry, and I could put on headphones and listen to it. And I had that. I had just a long wire in the backyard as my antenna. So I could listen to radio and stuff without actually buying a radio receiver because I had made a radio receiver. But it was cheesy. But then I spent money on a shortwave receiver. And I had just a cheesy little shortwave receiver, and I plugged my antenna into it, and I could pick up radio broadcasts from all over the world, and I would U.S. Postal Service mail receiving reports to the radio stations, and the radio stations would send you back a postcard. Yes, you actually received our program on this date, on this frequency. Here's our station. So I had what is known as QSL cards. So that's how I got into just radio. And
nobody told you about it? You just thought this would be interesting? You never saw it before. You just
no. I was listening to radio, and I was into radio as a device. And then when I found out for a little bit of money, I could receive radio from other places on the planet, and I thought that was interesting.
Okay.
So I listened to radio stations in South America and in Czechoslovakia and in Russia and in the UK, and I would send them QSL reports, and they would send me back QSL response postcards. So in the back part of my house, up in a closet shelf, I have a little shoebox, and in the shoebox there's probably 20 QSL cards from around the world.
Wow. I remember last time we talked about, or you talked about this, you had a lot of people in the audience were very interested in shortwave radio too, and hand radios, and compared them and that. And I don't actually understand, I'm sorry to say, I wish I understand a lot more than the last time I heard it, because I did pay attention the last time. Yeah. But I don't understand how the shortwave hand radios and the radio, how you can go from one to the other on this, because just look, it's the computer that allows you to do it, the software, I gather.
Yeah, it's the software-defined radio. It's the ability to tune to whatever frequency you want, receive it, filter it, and then demodulate it. So, for example, a ham that's interested in doing single sideband radio, where he wants to talk to someone, will actually speak into his desktop radio, which might be over $1,000. It will take his voice, convert that into an analog signal that is essentially on one side of the center line of a designated frequency. And so that's single sideband modulation. And that will go out to someone. Someone will hear it, demodulate it, speak back to them. That modulated signal will come back to his radio, and then his radio will receive and demodulate that signal back into a voice. And then he'll be able to talk with someone. So it's not just like one piece doing everything. You need a core piece that can tune and filter and demodulate. And then once you put a computer behind that, now you can do all kinds of magical things. You can do single sideband, upper and lower sideband, dual sideband, and that's just for the amateurs. And then you can, listen to FM radio stations, and it's all a matter of, once you have the signal in a digital form, you just need software to process it, and there are people out there that have created the software to process it, and all you've got to do is download their freely available plugins to do what you want. But when it comes to, I want to receive the James Webb Space Telescope.
Yeah.
Okay, people are actually doing that now. They're doing that using a software-defined radio, just like that little one. But the first thing you have to do is realize that the James Webb Space Telescope does not transmit in the range normally received by that $20 device. It transmits in the 8 gigahertz range. So you've got to have something that will map the 8 gigahertz range down to the 1 gigahertz range, so it then is receivable by the USB dongle. And that's a thing called a down converter. So, one part doesn't do everything. If you want to branch out and do something different, you might have to get some different parts to do that. But once you can get it all the way into the digital realm in the computer, somebody can write a plugin for SDR Sharp. It would be the James Webb NearCam decoder. And you can actually get images from the James Webb Space Telescope. So far, nobody's done that. But if the Webb telescope's going to be out there taking pretty pictures for years to come, I will not put it past someone to go learn about the modulation techniques and then write the plugin and demodulate it, because that's what NASA does themselves. they have very powerful radio receivers that bring in the signal, convert it to digital, and then process it. And they process it on the way up to modulate it, and on the way down to demodulate it. And then they take that raw data and they convert it into pixels in a picture. And that's how you get pictures. But that's how all of the spacecraft out in space do pictures. They take pixels, which are digital data, they modulate it, they package it up, they ship it over radio, they receive the radio, they demodulate it, they convert it back into pictures.
So when you first were listening to this. This was a listening device,
Yes.
and later on, I don't understand. Let's say that if I was listening to AM radio, I'm not going to be looking for the picture of FM radio.
No.
It's going to be wait until you go to outer space type of when you're going to want to see pictures of something out in outer space. And it's
not necessarily, because weather satellites produce pictures like that.
Yes. Okay.
I mean, they're not natural celestial organic objects, but they do have data that produces a signal that you can decode. And for weather satellites, you don't need an array of receivers. You just need one.
Now with weather, I'm thinking of, I think I understand on radio and sound coming, through, but I don't think I understand as to whether it has a sound. Not all weather has a sound. Like the wind doesn't.
No, there's no sound. There's no sound. It's just frequency and amplitude. For example, and here's one that's active right now. You and I are speaking not by voice. Our voice is being received by a microphone, converted to a digital signal, packaged up using a protocol, sent over the internet by software on your computer that then decodes that signal and then plays the waveform so you can hear my voice.
Yes, I understand that. But
that
if
was
I have
excellent analogy.
hearing wind, I wouldn't be sending you digital wind from my site. I don't understand how they pick up wind or rain. Well, rain does make noise, but
No. What they're doing is they're picking up the radar reflections of the atmosphere. So they send a radar signal up to the atmosphere, and it bounces off of raindrops and clouds. And depending upon the signal that they get back, they convert the individual data values into pixels for a picture. That's how they convert weather into a digital picture.
okay. Thank you so much. I know I took up a big section there.
No. That's exactly the missing breadcrumbs that people need to go, how do it do that? See, I'm a computer type, and I understand all this digital electronic stuff, so I can very readily connect the dots, which is why I was into. So if the professionals can do very large baseline interferometry, and they're just using software-defined radios and computers, it's just a lot more data. Why can't we do that? So I started writing the software to make it where those cheap little $20 dongles can receive the data, map it into a form that would be acceptable to collect large amounts of it, and then translate that data so that it's processable by the same algorithms, the same programs that they use at the very large array and worldwide radio telescopes. If I take my data and I just convert it to the format they're looking for, I can let them do all the back-end processing from our samples to create the pretty pictures.
I was trying to thank you, though, Monroe, when I was just finishing up, to say thank you, and I did appreciate the information about how you got interested in it and those postcards. And I wonder if they still do that postcard type thing when you listen to different stations.
I would think that shortwave radio definitely still exists. There are countries that still broadcast shortwave radio. And I would think that now that SDRs and SDR Sharp are out there, it's so much easier and cheaper than buying yourself a dedicated shortwave radio that, I would think QSL cards are still out there. In fact, you can just Google QSL card, and see if you have broadcasting stations that want to do it.
So much, and I agree with Helen about Sally. That would be very, very interesting. Sally's presentation on that would be great. Thank you so much.
I think that anybody that wants to present something, they just have to tell me what topic, and then I'll sort of pencil it into the calendar, and then they go off and do it. And if they want me to take a look at it beforehand, I can. But it doesn't have to completely follow what we're, logos and icons and format and stuff. It's content. I can always put wrappers around the outside of it and put that up on YouTube. Just realize whatever presentation you do will probably wind up on YouTube as publicly viewable. And I will remove technical foibles and No, I've given up removing my own ums because there's just too many of them.
Too many ums.
But we're giving an idea. We didn't know if Sally wants to do it because we were asking it, but.
Well, it's up to the person that's authoring it whether they want to sign up to do it.
It would be awesome homage to your father and your family, and we'll talk about a little bit of something that most people have forgotten. And civilization, as we know now, wouldn't exist without people like your father.
Yeah, he joined the military before World War II with the old Smokey the Bear hat and putties, leggings, and he did crystal radios and stuff when he was a kid as well. He loved that stuff.
I just think it's so amazing that we've moved from the giant towers that used 10,000+ volt spark gaps to transmit and receive Morse code on. And now we have mobile phones in our pockets that are far more capable than any radio that preceded it 20 years ago.
Incredible.
Yeah, he had at one time up to 7 radio shops, aircraft, Lunken Airport in Cincinnati, and two-way radio mobile for police, and ice cream trucks and stuff. Yeah. And so, he lost a guy with on a tower there when a tower collapsed as well, because you had to have towers to transmit.
Yep.
From base to base to base.
Yep. Nowadays they have enormous flat panels mounted on concrete structures, and you don't need those giant antennas all over the place anymore. Although they still exist and they still are in use.
Yep. And a lot of it was line of sight, which was kind of tricky for Cincinnati because it had 7 hills.
Well, there's still line of sight radio. The VHF radios, when they wanted everybody to convert their marine radios from AM to FM and use VHF instead of a AM band, there were a lot of things that just couldn't be done anymore because they were line of sight, and people forget that a boat might want to go out to sea farther than 12 miles. So it has to deal with the curvature of the earth. So you would have the Coast Guard saying, our antennas don't have to be as tall anymore. Oh yeah, they do, because if you want to be able to save people farther than 12 miles out, your antennas have to be higher because they have to compensate for the curvature of the earth. So there's some things you can't get around. The one thing that we've got around in antennas more than anything else is wavelength. If you remember, there used to be things called a full wave antenna, a half wave antenna, a quarter wave antenna, and even an eighth wave antenna. And you would have a wire that would have to be like, one factor of the wavelength of the radio signal you wanted to receive. So if you wanted to do shortwave on low frequencies, you might need a 50 or 100 foot long piece of wire to be cut to the exact wavelength of the center frequency you wanted to tune to. Think about that for a moment.
Well, that's what.
Remember when mobile phones first came out, they had that telescoping antenna on them, and then they went to a little short stubby antenna with a coil on them called a rubber ducky, a little stub antenna, and then they went to cell phones with maybe a 1-inch tall little antenna to a little bump that had the antenna inside of it. Where's the antenna now?
It's still there somewhere. It's inside.
It's in the
Well,
frame.
why isn't it big enough to do like at least a half wave of the signal? Because a half wave would at least be, several inches long. They discovered digital signal processing and analog to digital converters and digital to analog converters. And they convert the signal and then they chop it up using a digital signal processor to whatever signal they want. So the antenna they now have is called a fractal patch antenna. And if you actually took your phone apart, you'd see something that's about the horizontal and vertical diameter of a sugar cube. That's just a flat little piece that looks like printed circuit board copper. That's the antenna for your cell phone. And the particular pattern of little copper conductive spots is the fractal pattern. If you understand fractal geometry, that's a fractal pattern of the frequency that you want. And then they receive the signal, they digitally process it and digitally amplify it. And that's how your mobile phone no longer needs an antenna on it.
And then Monroe, one of my mentioning, like, because we've been watching the UFO kind of thing, that I have to post the link for the video just to show the people. So this is on YouTube. This is the Tear in the Sky, talking about a lot of the big name scientists, including 2 physicists that are famous, participating on that and getting the real deal data. It's like one more thing that I'm excited to hear it.
I know. I took a look at this, and the first problem I had with it is it opens with William Shatner.
Oh, come on. He's nice.
He's a paid promoter.
Yeah.
He did all those shows on the History Channel. The second thing I looked at was the other people that are involved. Some of them are starting to make sense. Neil deGrasse Tyson is the one that says, why is it we can't take pictures with at least a cell phone quality camera? And I, to a certain extent, agree with him. I think we ought to go at this full boat, as in, don't just use a cell phone camera, use a high resolution, broad spectrum telescope on a tracking mount to point at these things and get really good pictures of them and really high contrast ratio, and do it from multiple locations at the same time so you can triangulate. You can see, maybe slightly different angle views. You might notice that the Tic Tac is capsule shaped and not saucer shaped.
Oh, I got excited about the project because it's Kako and Loeb that are involved in the filmmakers because you have those filmmakers that don't actually know what they're doing. They could, don't have a good understanding of astronomy or imaging in like very long away, But then when you get involved like 2 respectable physicists that wouldn't put their names to destroy their own credibility, and that got interesting for me.
Well, I think it's well overdue for them to do some genuine digital instrument-based science observations of these things.
We're talking
Don't leave
about
it up
that,
to the military.
But we're not explaining what it is, so you should explain or show the video.
Well, they don't want to scare us,
They don't care if they scare us or not. And videos don't come through that great because I just don't have the computer horsepower for it. But if you ignore that, I will attempt to play the video.
But if you want to watch on your own computer, I posted the video on the...
Yeah, the link is in the chat.
What has made mankind is an insatiable curiosity. Insatiable. What is that? Nobody knows. The phenomenon.
Nobody's ever done this as far as I know.
It's a huge amount of work, a huge amount of data and equipment. That has never been done.
Whatever this is more complex than we could ever imagine.
This is a first in the field of ufology.
The variety of devices we're bringing as a team to study the phenomenon covered an entire spectrum of different technologies in real time.
That moment shook me to the core because I knew my life was about to change again.
I think we're going to have like a couple of really, really good spots.
When I hear that you've assembled a team of top scientists using state-of-the-art equipment, I say to myself, it's about time.
This is an unidentified, unclassified new phenomenon.
Wow, Tic Tacs. Navy Tic Tacs.
Maybe.
Caught on our cameras. Yep. That's incredible.
Crazy. It isn't crazy, it's crazy. It's crazy.
We can go from body heat to very cold, like about minus 62 Celsius or minus 80 Fahrenheit. Wow. We will be transmitting data up to 800 terahertz in frequency. Our highest technology is up around 500 gigahertz.
I can't tell you how much I'm looking forward to seeing what you've uncovered.
We're triangulating and converging at 2 points, the same object.
It's fading.
It's gone. It's gone. It's friggin' gone.
Saw something over Catalina. We need you up here.
We could be heading towards the biggest "see I told you so" in history.
That's what we need, the smoking gun that'll clinch it. That once and for all will settle the debate. No ifs, ands, or buts. And in the process, rewrite all of human history.
Oh my God, you guys. Is this the wormhole? It's insane.
Well, there you go. So I did like the matching shirts with the logos. That was a nice effect.
Yeah, I think it's going to be on May. I don't know which date, but it's going to be on May.
It'll show up on History Channel probably.
Oh, it's Tubi.
No, because initially it'll show up on History because History will pay them for the promotion of it. Michio Kaku doesn't speak for free.
Oh, okay.
Yeah. So they've already paid a lot of money to produce this video. And so once they get the data, they'll look at it. But you know me, I had to ask the questions like, okay, I see that you've got thermal cameras. I see that you've got some small diameter telescopes with cameras. I don't see any radar or LiDAR. So if you want to track something and know it's physically present, you need radar or LiDAR. And there are inexpensive vehicle LiDARs and radars out there now. You don't have to have, you know, like a military license clearance to have your radar or your LiDAR. And the LiDAR works in infrared, so it's not going to spook any pilot by having a green light shine in his cockpit. So it's a good starting
point. It's interesting that doesn't matter if it's visible light or infrared. If you have triangulation, you can have perfect distance. You can actually calculate the distance and the size of the object. That for me is the most interesting, because whenever we see something far away in the sky, because we don't have anything close, our eyes never know how far those objects are. We are very bad in measuring distances and sizes when we just look, except like pilots, they're well trained to do something like that. But even though you need other objects behind the object to actually have a notion how big they are and how far they are, and it's very hard to calculate that. And then having triangulation to show sizes and distances, how fast they move in the real data, even if the image is not that good. For me, sizes and distances are good enough.
Yeah, the particular place that they're looking at is 2 points along the coastline of Southern California and Catalina Island. So they're all accessible places. They're not that many miles away. But the UAP hotspot that the Navy's always talking about is south of Catalina Island. That's where the underwater UFO base is supposed to be, is south of Catalina Island.
Oh, I didn't know that.
Okay.
Is that where the Tic Tac was doing the cross in the water?
Yes.
Okay.
So now,
that's a perfect place.
Now you've triggered me. So you'll have to watch some stuff here. Let me bring up Google Earth and I'll show you with everything running. Wait a moment.
So if someone like Loeb or Cackle says like something like that, they're putting their careers on the line to actually say, yeah, we're not alone. So that will be the case for it.
So here's Google Earth. And I'm zooming up into Southern California. You can see Los Angeles, Long Beach.
Did you put that pinpoint, or it was already there?
Oh, I created
the USO base.
I took the data from our friendly Air Force pilot, and I used that to coordinate it. I took his triangulation information that he came up with. So they're going to be down here on the southern end of Catalina Island. They're going to be up here in Irvine, and they're going to be down here in San Diego. So that's their triangulation. But they're looking for something that's over here off the eastern side of Catalina Island. If you look to where the UAPs that the Navy videos showed, this is where they showed them coming up out of the water. Now, what you're looking at is Google Earth, and it has undersea sonar mapping images. So you're actually seeing the topology of the ocean floor in this area. There's a very deep canyon right here. Here's something interesting. Wait for it to finish drawing it. It'll take a moment.
No, I think the image is blurry there.
No. It just has to update it.
Okay.
If I go out and come back in again, it'll probably be fine. Come on. You can do it.
No, I think right there it's pixelated.
Oh, that creates a conspiracy all by itself.
Choo, 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 choo.
But what I was trying to show you here was, if that's really where the UAP surfaced out of the water, where it was like creating a bubbling spot in the water, there's actually something there. There are two giant underwater caves.
Or craters, like old craters?
No, think of it this way. The side wall of this canyon's going down, so this is actually horizontal, and these are holes in a horizontal side wall of the canyon.
Oh.
They're caves.
Interesting.
And I could swear that when I put that push pin in there, this was not fuzzy like this. It was just as sharp as what's above it. Somebody made it blurry, because it seems to be blurry right there.
But if you move like that, is like a, can you see if you move a little bit on the right, almost looks like a comb that goes this way. It's a fork. There is a part that is pixelated and then clear and pixelated again. It's on the left side.
Yeah.
If you go,
right there. You can see that there's a stripe. There's a slice right through here that's pixelated. And then the stripe narrows and it's still pixelated. And then the stripe is a little wider and it's pixelated. And then it comes out
in the
just
middle
fine.
of those two stripes is clear. Can you see it? That in the middle.
Yeah. So if I look above it, that's pretty good resolution for it to be sonar. This up here. You can actually see ridges in the sidewall of the canyon. And if I go below it, which is, many hundreds, if not thousands of feet deeper in the sonar, you can actually see little rivulets here where as the current, this is a very rapid current area, as the current flows through, it creates these little ripples in the sediment in the bottom of the ocean. And you can see them, but you can't see here. Curiouser and curiouser.
If I was doing it on my computer, which is sort of has problems at times, I would have to close it out and open it up again. And usually if I opened it up again the second time, for some reason, I don't know if it finds it faster or whatever, then it comes out clearer when I do things. I don't know. This may be, like you say, an odd thing, but I wonder if you closed it and reopened it, if it would maybe clear up.
The other thing I've noticed is if I go somewhere else, or if I zoom all the way out, then I zoom in somewhere else. See, it does take a moment for it to load, and then you get a high-resolution image.
Yeah.
And I can get high-resolution image down where I can actually see the tractor marks in the field. There's no problem with the image resolution of the computer.
No, I wasn't saying sometimes it's just like electronic thing or something, and then when I go back, it's cleared up. I don't know. Maybe it won't be, but I thought it would be worth a try before you would say, oh, well, there's something fishy going on here.
There are conspiracy theorists, and then there are anti-conspiracy theorists.
Yeah.
I don't think there's anything fishy in the ocean.
Yep, still seems to be that one spot.
No, it does seem to still be.
It's on a you don't need to know basis.
Yeah. Well, that's nice to know. For me, I wanted to know if it was just maybe an abridged, something that it just didn't load correctly. But it seems like it loaded.
I can even go in here and let's see options. Where's the cache? I can say clear memory cache, clear disk cache, apply. Okay. And now it will reload the image from the cloud. Still seems to be fuzzy right there.
Shape. Exactly the same shape. And what about those two fingers going to the side? You can see one line is blurry, one line is clear, and the other line is blurry.
Yeah, this one's blurry out this far. This one's blurry not out as far.
Yeah. And then
you can go right below it and still see all the detail in the rivulets, and you can go right above it and still see all the wall ridges on the canyon.
And what are they speculating that they're going to see here? They saw something come up from here.
This is a move along place.
This is the coordinates.
Move along.
This is the coordinates where they saw a disturbance on the water, and they saw a UAP come up out of the water from here. So I mapped the latitude and longitude from an Air Force pilot's reckoning of the mission, triangulated that down to this spot, and then zoomed in on what would be under the ocean at that spot, and I found cave.
If you scroll around the general area and even further out, there are a number of areas that are blurry like that. It's not just that one spot.
Yeah.
Could there be some kind of interference, like
it could be a bad radar. It could be a bad radar image. It could be they don't have any high resolution image at that level.
Yeah.
I like the conspiracy, but I tend to think
it is fun.
That I don't know.
Well, here's the part that they don't realize. The pixels are there. Do you see how sharp that looks from this zoomed out view?
Yeah.
They did not take, images every 100 feet as they went down to 1,000-foot depth. They took one image, and then the presenter, Google Earth, actually compresses the image and synthetically generates a different image as you zoom in. So the raw data still has all the pixels there. So it's, if the pixel data was there, then I can see it. If the pixel data wasn't there, I can't see it.
Landsat, that one is Geo SL OCP.
Well, this is U.S. Navy.
LDO.
This is U.S. Navy.
Yeah.
This is submarine mapping. The U.S. Navy actually conducts war games in this area because
where's the military base?
Onshore, San Diego.
Oh, okay.
Right in here. But the military conducts training exercises out here, war games exercises, because if they happen to drop some ordnance and it goes boom, if it goes 1,000 feet down in the ocean before it goes boom, nobody's going to notice it. But in the missions that they've been doing out here where they've seen UAPs, they've been completely unarmed. No gun rounds, no missiles, nothing, because they don't want to accidentally shoot each other because they're playing both the good guys and the bad guys. So they use radar lock as a signal of saying, gotcha.
You're calling it UACs?
UAP.
UAP, what does it stand for?
Unidentified aerial phenomenon, because UFO brings out all the people with aluminum foil hats.
Well, aluminum foil hat people may have been right about things when they
Yes, yes.
No, say it isn't so.
Has a hat.
And that's not the first time they changed the name. In the 40s, they changed from flying saucers to UFOs, and then now UFOs is the colloquial, and now they are changing for UAP.
Have they been reporting more incidences now that they're
every couple of years? Every couple of years, and they've recorded them. They've recorded them on the west coast of the U.S. in military operations, and they've recorded them on the east coast of the U.S. in military operations.
I mean, last year they sort of opened up the thing so that people wouldn't feel threatened by their jobs if they lost their, you know, they said now we're going to record things. You did a presentation on it.
What I recorded was to avoid Air Force pilots coming under scrutiny. They've been using their personal mobile phone cameras to record UAP evidence, because if you remember from one of the videos, there was UAP evidence from the infrared cameras aboard the military aircraft, and that data got removed from the aircraft carrier by some guys who showed up in a helicopter shortly after they detected the UAP.
This is recently?
A couple of years ago.
Oh, okay. Because I thought it was like last year or the year before last that you did the presentation that it was like there was a big hullabaloo about that now the United States was going to now recognize UFOs. And
yes,
then when
I did that presentation last year, and the video was from 2 years prior to that. So 3 years ago from today.
But now that sort of was supposed to free up people to say that you're not going to lose your job if you report UFO.
Yeah, sure.
It's still a lot of pilots, like commercial pilots, they're not doing it. Afraid still, because things are moving very slowly.
Commercial aircraft pilots will still not report UFOs to their parent airline because they do get scrutinized, they do get shift changes, and they can be, well, we're cutting back. We're just going to terminate you and a couple of other guys.
First videos came on 2017, and just this year that the New York Times and the CBS did the 60 Minutes show. It's like it's moving very slowly because some people are afraid to open their mouths because they're going to lose their jobs. Some people are threatened by that. It's like it was recent. The guy was like
he was the guy that led the U.S. military's UAP program. Some say he was fired. Some say he quit. I think they came to a mutual understanding that he wanted to let the public know what's out there, and the government didn't. And then the Navy, after 2 years, came clean with, yes, we took these videos. And then the U.S. Congress got all over the Navy for having released this information to the public. And now the Congress had to be seriously wanting to know more. And seriously wanting to know more produced a report that says, we don't know what they are. Could be Chinese, could be Russians. But they wouldn't say they are UFOs or they aren't UFOs. They would just say, we don't know what they are, but they can fly faster than us, they can maneuver better than us, and they come and go like disappearing, and we can see them on radar. So they're physically there, they maneuver better than our best jets, and they can pop in and pop out. So why wouldn't you consider that a military threat if you're postulating that China or Russia had this ability? They could literally pop in, waste our aircraft, and then pop out. Wouldn't that be a threat that you'd want to investigate seriously?
Well, Marco Rubio wants to do that.
He was
he already
2 years. No, 2 years ago when he was in Congress, he worked on the U.S. House of Representatives Security Committee, and he's the one that helped to file the request with the Navy for more information. But he didn't file it with the Navy. He filed it with the Department of Naval Intelligence, the DNI.
Okay.
What?
For anyone who wants to say more things, because we're gonna need to sleep early, so there's 23 hours and 54 minutes.
Yes, you have about.
We have 6 minutes.
Yeah, you have 6 more minutes to talk before we have to cut it short, because I'd like to get some time to sleep before I wake up at the crack of dawn tomorrow.
What time do you have to get up?
Well, if I'm going to pick her up at 9:30, I have to leave the house at 9, which means I probably get up about 7:30.
No breakfast?
I'll probably have a quick bowl of cream of wheat with Honey Nut Cheerios in it and some grape jam and maybe some...
I'm sorry I asked.
Yeah.
It's like, you know, 6 years old breakfast. Oh my goodness.
No, it's fresh. It's not 6 years old.
Yeah, and then later, while he's driving to my house, he's drinking the radioactive liquid.
Yes, I have to stop and pick up some of that on my way to you.
What is radioactive?
Right now I'm drinking this horrible tea mixture.
He drinks Mountain Dew that has caffeine.
Yes, caffeine and sugar and orange peel essence, and yeah.
I love Mountain Dew.
Yeah, do the dew. Okay.
Well, that's nice to know. And with that, I'm going to say good night so that
all
you
right.
can get up right.
Anything else before we close? Anything else before we shut off the recorder? Anything else before we close?
Just have a good time tomorrow.
Okay. I'm sure Helen will do video and pictures and things like that, and I'll just bake in the sun.
All right.
You know, there's a way to see the air show at home.
Yeah, I know. Air.show.com.
Yeah.
Yeah. But it's much better when you can feel them fly directly overhead.
Yeah.
Like you're trying to drink and the airplane goes through your head and you drop everything in your clothing. Well,
I have to warn you, you know, when they circle over that way and they go to the west, they're going to be coming back over your head to the east. And I guess she didn't believe me until they did that once when she was drinking something. The
noise level, though, is just hard for me.
Hey, they're practicing at Executive Airport 5 minutes from my house. I can't avoid the noise.
And I'm in a flight path. They come through my house. I can see the shadow of the airplanes and my house shakes. I'm right in a flight path.
Yeah. I think they use 15th as their north-south cross pattern. And for east-west, I think they use Cypress Creek. Anyway.
All right.
Okay, good night.
Good night.